Hello, good morning. Today is August 18th, and it's around 3:20 a.m. Dallas, Texas time. And I am giving this placeholder presentation for a keynote address that I will be giving in about 2 hours, which is 5:20 a.m. Dallas, Texas time, 5:25 a.m. Dallas, Texas time, which will be around 11:25 a.m. London, UK, Manchester, UK time. And so I'm going to give, as I said, this placeholder presentation. And usually what I do is record a presentation in case there is a technology glitch. And I email the presentation or send the link to the conference organizers. And again, in 2 hours, I will be giving the official keynote presentation. And I'm Dr. Bhavani from the University of Texas at Dallas. And again, thank you very much for listening to this presentation. So what I'm going to do is share my screen. Let's see. Okay, now where is my presentation? Okay, so the talk I will be giving will be at the International Conference on Cloud Computing and Big Data. So it's, I believe, ICCBDC. And my talk is going to be policy-based, privacy-aware, assured information sharing in the cloud and IoT. So I work at the intersection of cybersecurity, cloud, and data science / machine learning. Okay, so the outline of my talk, first topic is going to be big data security and privacy, because it's at the very foundations for cloud and IoT security. And my second topic will be policy-based, cloud-centric, assured information sharing and governance. And then I will move on to a topic such as from cloud to social media to IoT and data security and privacy life cycle for IoT-based systems. And there's also this whole new concept, social IoT, and as well as vehicular social networks. Okay, so my first topic is big data management and analytics that pertains to security and privacy. So the pros and cons, why do we need to manage big data and analyze big data? So again, lots of technological advances, novel applications. It's possible to capture, process, analyze large amounts of data for numerous tasks like healthcare, finance, marketing, and so on. It's also very useful for security applications. So for example, if you want to do user authentication, access control, anomaly detection, user monitoring, and protection from insider threat, right? You will need to use big data analytics is really very useful, and it contributes a great deal. So analyzing and integrating data collected on the web, you can identify connections and relationships among individuals, and that could in turn help with homeland protection, disease outbreaks, and so on. And so one of the challenges we have, collected data, even if anonymized, right? You can have different records, and you have anonymized both records when you put it together, right? When you link multiple records together, you can re-identify the person. So privacy could be violated. Security tasks such as authentication and access control, that could require, say, 2-factor authentication, 3-factor authentication, biometrics. So a lot of sensitive information could be divulged. And the information misused or stolen can lead to privacy breaches. So on the one hand, big data analytics, management and analytics, tremendous use, numerous applications, including cybersecurity, and I'll give you an example later on. But there are privacy violations, And one thing to note is that big data analytics, while it has numerous applications, these analytics techniques, data mining or machine learning, these techniques could also be attacked, right? So what do? Because if your machine learning techniques are attacked, then you could have all the wonderful machine learning algorithms and so on, models, but if they are attacked, they are going to produce incorrect results, and there could be disastrous consequences. Okay, so privacy enhanced techniques. So I'm giving some major topics. So again, I organized a workshop actually on this topic about, let's see, it's 9 years ago, National Science Foundation workshop on big data security and privacy. So we had a lot of discussions on privacy, and privacy enhanced techniques have been proposed, ranging from cryptographic techniques to data anonymization, and then privacy preserving record matching. So what we did here was, when you have different records and when you put them together, as I mentioned, the individual, the identities of the individuals could be compromised. And so how do you do it in a privacy preserving manner? Okay, so that's what the second bullet is all about. And the third bullet is privacy preserving collaborative data analytics. So different people are working together and they are collaborating. And so how do you ensure privacy? So for instance, see, we all have a secret, right? And so we could encrypt the secret and put it in a basket. So my secret could be, I have COVID. Your secret could be, you have cancer. Another person's secret could be, he or she has AIDS. So we don't want to divulge the individual secrets, but collectively we do analytics with encrypted data, and the results of the analytics. People who live in Dallas, Texas, there's a higher incidence of, say, lung cancer, right? So then you can, carry out some public health activities. And then there's also privacy preserving biometric authentication, right? Templates of user biometric representation, sensitive information, reasoned approaches address the problem of using combination of perceptual hashing, classification, and zero knowledge proof of knowledge protocols. They are called ZKPK. And we need scalable techniques to reduce the false rejection rates. Okay, so we came up, that means we means the conference participants, we need to develop a multi-objective framework for different dimensions. So sometimes security and privacy could be crucial. In other case situations, we want utility, because what's the point if you want to mask all the data, almost everything, so that the data becomes useless, right? So you need utility. And then the cost, because if it's so expensive to maintain security and privacy, then you need to think twice, right? So you want to minimize costs, right? Minimize the risks. So it becomes a dynamic programming problem. So you want to minimize the cost, right? And maximize the utility given the risk and cost constraints, and minimize the risks. So how do you come up with a dynamic programming model so that you can get the maximum benefits? So you need to understand the right definitions of privacy risk for data sharing, probability of re-identification, given certain background knowledge may be a right measure of privacy risk. So again, this is sort of the conclusion the workshop participants arrived at. Now, I mentioned that I'll give you some examples on how big data science, big data for cybersecurity applications. So cybersecurity applications could be anomaly detection, intrusion detection, but because we are having to deal with big data, large data streams, so streaming data arriving continuously. We can use past data to build classification model, predict the labels of future instances, and helps with decision making. So you can ask the question, so what's the big deal? We've been doing this for 30 years. One thing to note, big data streams, continuous flow of data, very common in our digital world, massive amounts. But the problem here, because of massive amounts of data continuously arriving in streams, concepts are changing. So today it could be buying Microsoft stocks, tomorrow it's could be Google. Next day, it could be Facebook and then Amazon. And the following day, Netflix. So every day, things are changing, right? And so what do? Streaming data arrives. So we have to build. One model does not fit all. So we've got to build an ensemble of classification models, right, as concepts are changing. So sometimes concepts get old, and so those models are thrown away, right? And so what do we do? So in this particular case, we look at attack traffic, right? If it's an attack, right, then you block and quarantine. Benign traffic, you let it go through, but the models are constantly being updated, and you can have a human in the loop, right? But the whole idea of our ensemble-based model is that we can do this. We try to do it without the human in the loop. But always for machine learning, it's always useful to have the human in the loop. Okay, so now remember I said the machine learning techniques, big data techniques could be attacked. Then you cannot rely on them anymore. So adversaries trying to learn about what we are doing. What's our model? What sort of data are we using to train the models? So we have to understand what the adversary is up to. It's not concept drift. It's not online learning. Adversary adapts to avoid being detected. So it could happen during training time, during test time, modifying features when data mining is deployed. So essentially, we play a game between the adversary. So in this picture, this middle line, right, is, so we are using support vector machine, which is a data mining machine learning algorithm. The red squares are bad instances. The purple here are good, purple or blue, whatever you see, good instances. What the adversary is trying to do is learn as much as possible and trying to push these red squares below this boundary line so that they won't be caught. So look what happens. 1, 2, 3, 4, 5 bad instances are not caught. So we have to now thwart the adversary. And so this is adversarial support vector machine. We were one of the pioneers, but now and that was like 11 years ago. So many people are now working. One of the most hottest areas in machine learning and cybersecurity. So threat model, attacker modifies X to X prime, modify packet length by adding dummy bytes, good word to spam, noise to an image. So what happens? We have this dotted line, right? That's the original support vector machine. So the red crosses, right, are bad instances. Green circles are good instances. It's just a little bit of opposite to what I showed in the previous chart. So the adversary is trying to push the red crosses to the other side so they won't be caught, right? So what do we do? So here it's better explained, right? Red crosses, green circles, but adversary is trying to push it beyond. So these are all the black crosses here are the bad ones that we are not catching, right? So what do? We learn the adversary's method, and then we move the support vector machine boundary line to here. Now, so if you move the boundary line to here, all these black crosses, right, that were not caught earlier, now they are going to be caught. So you can ask the question, why don't we move the boundary line right here? Then we can catch all the bad instances. But remember what happens. If you move it right here, all these green circles will also be noted as bad instances, whereas they are good instances. We don't want false positives and we don't want false negatives. So black dashed line is the standard support vector machine classification boundary, and the blue line is the adversarial support vector machine classification boundary. Okay, that's the blue line. So this gives you some sort of idea as to sort of work that we've been doing. Okay, now that's part one. So now policy-based, as I said, privacy-aware, policy-based, privacy-aware, cloud-centric, assured information sharing. Okay, so that's our second topic. Now, what's our approach to information sharing? Again, assured means secure information sharing. So again, policies are governing everything for us, okay? So we have looked at policies, and then sometimes people don't share, so we give them incentives. And so we had lots of real world data, integrating Medicaid claims data, and we mined the data. And so we enforced policy. So we divided our partners into 3 types of partners. And so between trustworthy partners. So sometimes I work with colleagues who I trust in my team. And so sometimes they don't share everything, and I don't share either everything, but still we want to give incentives. So we enforce policies and determine how much information has been lost. So we try to measure, right? By enforcing policies, we are not freely sharing. Okay. So we have to determine incentives and risks, because we don't want to share everything because there are risks. So a second team, they were looking at semi-trustworthy partners. So they said that, okay, I want to give you something, you give me something. It's all becomes game playing, like how I mentioned here, right? Between us and the adversary, there's game playing going on. So we all want to benefit. And the question is, who wins the game? Of course, we also have to work with people who we don't trust at all, because, we may be in the same department, and, they may steal the ideas. Fortunately, that's not in my department, but they may steal our ideas. So we conduct active defense and determine the actions of an untrustworthy partner. So we defend ourselves from our partners using data analytics techniques and active defense. So we want to monitor them. So I'm not going to talk about 2 and 3. My main work was only focusing on 1. So I'm going to talk about, so first what we did was we didn't use any cloud. So we looked at policy and incentive-based information sharing. So we enforced policy. So we had integrated Medicaid claims data, removed the identifiers, and we enforced policies. So we enforced policies. So we used, there are different databases, all Medicaid data in the state of Texas, identifiers removed. And we had XACML, Extensible Access Control Markup Language. That was our model. And so we used it as our access control information sharing policy model. And then we said, okay, in one case, we had these policies enforced. In the other case, we didn't have policies enforced. And so we compared the data shared, and we came up with a measure as to how much information is lost by enforcing policies, right? So, of course, we have to enforce policies because we can't freely share information. But then if you openly share everything, right, by enforcing policies, we are losing some information. So this whole experiment was for 2 purposes. One is to show that XACML can enforce these policies and we can share. Remember, this is not a cloud yet, right? It's just a distributed environment. And we also wanted to show that by not enforcing policies, we are freely sharing. So we can measure how much information is lost by enforcing policies. And then we looked at incentives. We gave some incentives to partners as to make them share more information. Okay, so that was an experiment. So now we move to the cloud. So on a separate project, we developed a secure cloud. So this project was developed, it was several years ago, about, around, we finished this project probably around 7-8 years ago. So the cloud has virtual network monitor. So we assumed that we have a virtual network monitor, and we didn't look at security because we couldn't finish everything. It was only there's a project scope. So we focused on the other layers, right? Virtual machine monitor. We used the open source, Zen system developed at University of Cambridge, secure cloud storage manager, Hadoop MapReduce, data manager based on the cloud. We used Hive, and we used semantic web technologies and the user interface for the applications. Our applications example was information sharing. And of course, we had policies, quality of service, sometimes security is important, sometimes performance. So, and then cloud monitor the cloud. I'll give you some examples. And then what are the risks and costs involved? So the ones in blue, we have completely finished the projects, and the others are still ongoing bits and pieces. The major parts are completed. So you can see Zen, which we secured, looked at security issues, secure Hadoop, secure MapReduce, and secure Hive, secure SPARQL, and then the various types of applications. Okay, so what are the types of policies? So we only focused here on information sharing. but also access control policies, privacy policies, governance policies like audit policies, regulations, compliance, and then integrity, data quality. We can go on and on, but I'm going to focus on data sharing. So what are data sharing policies? So agency one, so again, now we bring policy experts, right? At that time, we are computer scientists coming up with some kind of toy policies. So agency one shares resources with agency two, if agency two also shares its resources. So like John telling Mary, okay, I will share with you, provided you share with me. It's like very childlike policies. So if I want to share, if I get a request from agency to share information, I will say, give me justification. So agency one tells agency two, I will share with you, but don't share it with agency three. So Tom is telling Mary, I will share with you, provided you don't share it with John. And agency one shares with agency two, depending on, up to a certain time. And then we have this inference problem. So we do some analysis. If I share this information with agency two, based on the background information, will agency two be able to infer something that is highly sensitive or private? And, the social media sharing as well, we looked into that as well. Okay, so we developed two prototypes, actually. So it's a joint project between US, UT Dallas, and University of Insubria in Italy, and King's College, University of London. So we have studied clouds based on Hadoop MapReduce, more recently also Spark, query rewriting. So the challenge for us is, how do you rewrite the queries and optimize them according to the policies? And we looked at relational data, and for that we used Hive. It was originally developed by Facebook for their internal use, and then they made it open source. And then we also looked at RDF data, resource description framework, and RDF, because for images and geospatial data, RDF is better representation, but we had to do much more implementation for that, and I'll explain to you. And SPARQL is a query language for RDF. That's a semantic web. And initially, we demonstrated with XACML policies, Extensible Access Control Markup Language. Okay. So we joined demonstrations. First demo, each party submits the data and policies. And the cloud was in Dallas. And so we managed the data and policies. The second demo, of course, we used multiple clouds. The cloud could be anywhere. So the first architecture is access control with Hive. And so this is the Hadoop, secure Hadoop. And then we looked at we looked at security aspects for Hive. And then this is our policy engine, XACML. Fortunately for us, Hadoop was there, Hive was there, the relational database. So we just had to look some security issues, and we implemented the policy engine, right, for the relational data. So we can create views and upload XACML policies. Users can define views only if they have permissions for all tables, and so on, various types. So our paper here explains, and we have written quite a few more papers since then. So that's relational. But with semantic web, because for multimedia, geospatial, and so on. So one thing I've got to tell you, it's like comparing apples and oranges. Here I talk about the system architecture. And here I talk about the functional architecture. So we had to generate a lot of data. So we used the data generator that was developed by Lehigh University. And so here is the left-hand side is all the data generation and splitting based on RDF. And the right-hand side, right, is all of the XACML policy engine, right? So what we also had to do is, because we didn't have, remember, for the relational data, we had Hive. But for our semantic web data, we didn't have a Hive equivalent, right? So we had to develop a data engine, SPARQL query that will accept SPARQL queries, because Hive is based on SQL, and RDF, the query language, is SPARQL. So we had to develop our own SPARQL query optimizer, and then implemented the policy engine. And so we did a demonstration, and with both Hive and SPARQL Query Optimizer, 3 agencies, so Dallas, London, and Insubria. So we found that performance was not good. And we figured part of the reason we are mixing and matching technologies. Relational, semantic web, XSEML is based on XML, this is based on RDF, so all these different data types. So we said, let's just focus on one thing. Let's do it, because we need, RDF can be used to represent relational data as well as semantic web data. So let's just work with RDF. But we didn't have a policy engine. Remember, there's already XSEML implemented. But for RDF, we didn't have a policy engine. Fortunately, one of my PhD students had developed an inference, completely separate project, an inference controller, essentially a policy engine. So for semantic web, they used Jenna, developed at HP Labs in Bristol, England, RDF documents, inference engine rule processor, Pellet is from College Park, Maryland, and policies ontology. So the user comes in, and according to the policies, looking at the data, and the inference engine will process the, according to the policies, get the data, determine will the user get, can the user get additional information through inference. So we had a nice policy engine, but it was not implemented in the cloud. So we took this policy engine, re-implemented the whole thing in the cloud. When I say re-implement, we didn't just port it, P-O-R-T, to the cloud. That means it will just sit on one node. We had to completely re-implement and parallelize it to take advantage of the virtual machine technology and so on. So it was quite an effort, but we were successful. And then we demonstrated everything is now in RDF and one cloud between London, not one cloud, multiple clouds. Remember, earlier we had just one cloud here. But now here we have multiple clouds. It could be anywhere. Dallas, London, and Insubria, Italy. And so we demonstrated sharing information according to those policies. Okay. So we did a lot of other extra work. For example, how do you, because remember, a lot of additional projects, small projects we did. So one was on query processing in a hybrid cloud. So what did we mean by that? So hybrid cloud is a private cloud and public cloud. Private cloud, the company like IBM and so on, big companies and government agencies, they have their own cloud. Public cloud is the Amazon AWS, right? And so how do you split the data, right? Which data goes into private cloud, which data goes into the public cloud? And so several key challenges, right? We have to look at the cost, right? Solution must account for data representation, monetary cost. What are the costs? Because using public cloud, we'll have to pay some cost, but private cloud also, we have to build the cloud, right? And so what about query processing? How expensive is query processing? How much time it takes? And so based on all that, we came up with, again, it's a dynamic programming problem, right? Based on the cost, based on security and privacy and the utility of the data. So it's usually the security, privacy, and the risks, utility of the data, and the cost, right? And based on the dynamic programming, we decided how to split the data. That's one project. Another project is conducting cloud forensics. So what we did was we had Linux, guest operating systems like Linux, Solaris, XP. Zen was our virtualization, and then, of course, the hardware. And then we looked at, where do you put the antivirus, right? Should the hypervisor, right? The hypervisor, should it monitor all the guest operating systems, or should each guest operating system have an antivirus product that's going to monitor? So we looked at all these. We applied some formal methods, integrity via inline reference monitor, and forensics data extraction in the cloud. Okay, so we can see how forensics is done. Then the next project, okay, so up to this point, we talk about how do you secure the cloud, but now we can use the cloud for security, like malware analysis. It will significantly improve the performance. So what did we do? We took one of our old machine learning, previously implemented machine learning algorithms, and that is, for malware analysis. And that's where we extract engrams and so on. There were so many features. It was so time consuming. So we So we took that algorithm again. We have to re-implement, because if you want to get maximum advantage from the cloud, you've got to re-implement all the algorithms. So we re-implemented them in the cloud, and we found considerable performance improvement. Okay, so that was another project. And then, of course, when you talk about the cloud, there's cloud governance. And so I wrote a paper, one of the early papers on cloud governance, and published it, I think, about 3 years ago. And a book has just come out. Very good authors. I'm actually reading the book on cloud governance. I think one of the first books on cloud governance. And so I should have given the reference to you. But in any case, I think the Meredith Stein, she's one of the co-authors of the book, right? So, and there are 2 other co-authors. So what's cloud governance? The main question is, when you have to govern the cloud, who is responsible, right? Is it the cloud service provider or the person, the company that is using the cloud? So first, we believe that every CSP, cloud service provider, I'm just talking about some excerpts. I give a huge mini tutorial I give on cybersecurity governance and cloud governance. I teach this course in our business school for the Institute of Governance. So we believe that every CSP must have a governance strategy, right? When you are managing a cloud, right, you better have a governance strategy. So this could have statements like, is the cloud compliant with the various regulations and laws and privacy policies and so on. So organization that is using the cloud also has a responsibility towards the governance, right? The organization has to ensure it's not being careless, deploying attacks on the cloud via malware, and so on. Finally, who is responsible, right? Should we have a chief cloud officer? We have chief information officer, chief information security officer. So do you want to add one more person? Okay, these are all questions. And then, of course, for cloud governance, you have to protect the cloud against privacy attacks, cyber attacks, and privacy violations. Protecting the cloud against cyber attacks and privacy violations, it should be a top priority for the cloud service provider and the organizations as well. Once you put your data in the cloud, right, then how can you ensure your privacy and your security, right? How can your data be prevented from being stolen or maliciously corrupted? There are risks unless you keep the data encrypted and work with encrypted data. Theoretically, with homomorphic encryption, it's possible, but it's still practically not feasible. Every CSP must provide some assurance regarding the security and privacy. The clouds must be certified by some trusted authority, certification, accreditation. Appropriate cloud governance policies are crucial, and the idea is to carry out risk analysis for various computing systems with respect to cyber attacks, and subsequently utilize various risk and mathematical models and compute the insurance. So you have to get cyber insurance. Who has to get the cyber insurance? Of course, cloud service provider. What about the organization using the cloud? And one more thing, you can't have a cloud strategy separate from the business strategies. Security strategy, AI strategy, data strategy, cloud strategy, they've got to be aligned with the business strategy. Otherwise, corporations, the bottom line is business. Since most companies are moving their data and processes to the cloud, a cloud strategy has to be integrated with the business strategy. This means any risks as well as security and compliance issues for the cloud have to be taken into consideration when formulating the business strategy. The loss of data in the cloud or attacks in the processes will have an impact on the cyber insurance, and as a result, the revenues may be impacted. Therefore, we need cloud and cybersecurity experts to work with the business analysts to integrate the cloud. So if you have a cloud officer, a chief cloud officer, he has to work with the information security officer, financial officer, and all these officers have to work together. Okay, so now I come to the third part of the presentation. From cloud to social media to IoT, data security and privacy lives. There are many topics that I've put together, combined. So IoT, Internet of Things. There's Internet of Healthcare Things, Internet of Financial Things, Internet of, what else? Transportation. So right now we have a huge project that we are working on, and that's Internet of Transportation for the Department of Transportation. So in my previous lecture, I think last year, I talked in the previous keynotes, I focused on Internet of Transportation, but I'm just briefly talking about, here you have Internet of Home things, right? Your tea maker, your clock, your coffee maker, your television, your Amazon thing, all of them talking to, and your iPhone talking to each other. So here you have your cars talking to the trains, to the trucks, and so on. That's Internet of Transportation example. So what about the cloud-based Internet of Things and security? So mobile devices, smartphones rapidly becoming extremely prevalent, billions of smartphones, right? I think just over a billion, but it's much more now. Ever-increasing popularity of smartphones used in the multiple applications, including monitoring of personal data, health, food intake, exercise. With the emergence of quantified self, personal data collected and various devices, wearable smartphone apps, and so on, right? Give guidance to so much of data out there. And quantified self, of course, is very important because, they're collecting a lot of data about us and giving us advice, right? I love vanilla ice cream and milk chocolates. Wouldn't it be great when I open fortunately, I don't keep anything in the refrigerator, vanilla ice cream, right? Or milk chocolates. But wouldn't it be great if I open my refrigerator and there's an alarm that says, no, you're not supposed to eat that, right? Data collection and sharing often carried out without the user's knowledge. To address this ever-increasing challenge caused by digital world we live in today, we need regulations for privacy. Okay, so again, the quantified self, right? So I'm more or less, sort of repeating what I've said, mobile devices, billions of users. The quantified self movement is very good, right? We carry our Fitbits and our glucose monitor, personal life habits. Giving me advice, giving each of us advice is very good, but imagine privacy is violated. So if, say, they find that I've got diabetes or something like that, fortunately I don't, then they may not just deny me coverage, but deny coverage for my son and for my grandchildren, right? So data collected by device, privacy is important. Device monitoring, right? It can cause havoc. Such privacy violations could easily get out of control if data collectors and aggregators, right? Financial and health-related data with tweets, Facebook activity, and so on, so much of information. So how do you do? We need quantified self, right? That's very important, but we also need privacy. So we are saying privacy-aware, quantified self, cloud-based framework. So health-related, fitness data, location, social media, all of that is collected in our smartphone, data collection, data storage, and so on. Cloud is crucial because we can't put lots of stuff in here. A lot of stuff has to go into the cloud and maybe an encrypted cloud. Anonymized data. So this is our privacy aware. So what we are saying, and we have designed the system and implemented some aspects. So policies have to govern data collection. Policies have to govern data storage and access. Policies have to govern data analytics and also data sharing. I talked earlier about data sharing. So data collection. So when I collect data from somebody, I'll say, okay, I will only keep the data for the study. That's until the end of the month, 1 month or 1 year. After that, the data will be discarded. And you better stick to it, right? Otherwise, the consequences could be, really bad for you. Okay, so policies have to govern. And so what we did, right? This is a thing that we designed and implemented. The cloud is storing, some of the data. As more data collected, storage on the device will not be sufficient, so we need to use the cloud. And again, based on access control policies, local applications running on the device will be given access to some of the collected data. When needed, these applications will be allowed to access, right, the encrypted data stored in the cloud. In some cases, the data may not be needed in fine grain. So if you're 20 years old, you can have a huge meal and you don't have to weigh yourself because, you put on 5 pounds. It's not taxing for the heart. But if you're 70 years old, or even 80 years old is worse, you eat a lot, and then you could get a heart attack and die that night. Or you've got to weigh yourself every day, right? So don't collect unnecessary data, but collect data that is important and vital. In other cases, data may have to be deleted to preserve privacy. How do you know you have deleted the data? Right? There has to be some audit policies. And we envision Right. So in some cases, right, generate fake location data to hide the fact that person participated in a protest, all of that. We envision that data sharing and analytics will be carried out using services running in the cloud. Based on different scenarios, some data could be encrypted, some may not, and so on, right? So that's the privacy aware. Now for Internet of Transportation, so that's one type of, so that's healthcare, Internet of Healthcare things. For Internet of Transportation, we developed a system and for drones as well as for cars, ground vehicles, and for air vehicles, not for the sea vehicles. So we had a three-step process. The first thing is to model the autonomous vehicles invariant. So this is done by someone, a control engineer, right, who understands the model of a car, right? Mechanical engineer, control engineer, electrical engineers, and so, but we are computer scientists. So this is a bit beyond me, at least, okay? So we work with my colleagues, and so we developed this model. So for example, AV's invariants are calculated using well-known nonlinear models, accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis for the aerial vehicles, and vehicle positioning steering angle for ground vehicles. The online stage, we use the extended Kalman filter, is used to predict AV's physical behavior by eliminating unknown parameters from noisy sensor input. The algorithm is divided into two sections that predicts and corrects the estimate before it is compared against the sensor data. So then we have the third part is anomaly detection. A CUSUM, a statistical algorithm, is used to detect persistent attacks. Alarm is raised. So you could ask the question, what's the big deal, right? Pre-processing, online, and anomaly detection. The challenge is for this particular application, getting the model correct and understanding the attacks to this type of data, right? So we have, you know, certain types of attacks for certain types of systems. That's the challenge. And so paper describes several aspects. And so our implementation, we did it for drones and cars. So for aerial, AV Intel Ready to Drone Controller PX4, focus on detecting GPS spoofing. So one type of attack is global positioning system spoofing and gyroscope. GPS attacks are deleted after 0.2 seconds, while gyroscope detected after 1.5 seconds. Overhead introduced 5.4332. Ground AV, custom built on top of Traxi Ford Fiesta, ST Rally chassis. So we had, again, overhead here was 5.4, and it took a while to detect, 1.5 seconds. So quite a bit of overhead. For ground, focus on detecting visual attacks on the camera. Attacks detected after 0.1 seconds. Overhead is 2.25. Each threshold produces a probability of false alarms of approximately 2%. Okay. So that's the security aspects. Privacy, what do you do about privacy? Without a doubt, we really need to use machine learning because it will give us information about driving patterns. It will give us advice and also give us information about things like the congestion, traffic, and so on. But because of machine learning, right, privacy could be violated. So what we are saying, and the thing is, adopting new technologies, if we know that there's some level of privacy, then people will be more open to adopting technologies. So we haven't implemented this, but we want to take a similar approach. Like instead of a smartphone, we have a car. Inside the car, we have data collection, some gadget, data collection, storage, analytics, and type of data, not the healthcare, fitness data, radar, GPS, cameras, LIDAR, ultrasonic, and some data is locally processed, some in the cloud. So very similar approach. Privacy-aware, policy-based framework. Okay. So now there's also social IoT, social Internet of Things, vision, challenges, and trends. There's a very interesting paper. As stated in the above reference paper, IoT describes new world, billions of objects, intelligently communicating. One of the important areas in this field, new paradigm, social Internet of Things, new concept of combining social networks and IoT. SIoT is an imitation of social networks between humans and objects. Objects like humans are considered intelligent and social. They create their social network to achieve their common goals, and authors It's a survey paper. But something to know, there's also vehicular social networks, all the vehicles, right? Talking to each other, helping each other, telling us where to, get accommodations if you're stuck overnight. So this will be really good. But again, I'm really worried our privacy could be violated and there could be scammers. So that's my major concern. Okay, so again, assured information sharing with vehicular IoT. Remember, we said multiple agencies. Instead, we also have AVs, AV1, AV2, AV3, autonomous vehicle 1, vehicle 2, vehicle N, and they're all sharing data. Can we bring our cloud infrastructure that we developed into this environment? My last chart. Okay, so I've talked for about, I think, 45 minutes. So developments in integrating cybersecurity and big data, AI, ML exploding, applications of AI for security inside a threat, and security for AI adversarial machine learning, right? Developments in privacy-aware healthcare management lifecycle, same time development, Internet of Things, including transportation, right? Security, privacy solutions, mainly physics-based. Driverless cars become reality. More AVs will use AI, ML. How can we develop AI solutions? How can we develop a privacy-aware, policy-based data management framework for Internet of Transportation and infrastructures? Numerous opportunities for substantial research and development. Okay, so you can contact me, my email address, and I'd like to thank my colleagues, Latifa Khan, Dr. Latifa Khan. He worked with me on data science. I worked with him actually on data science for cybersecurity. Professor Murad Kantarjalu worked with him on adversarial machine learning. Professor Alvaro Cardenas on Internet of Transportation, and Ms. Rhonda Walls, who is our project coordinator. And again, thank you very much for giving, and I'm going to stop sharing the screen. Thank you very much for giving me the opportunity to give this keynote presentation. And I will see you all in actually just over an hour. And so I'm going to stop the recording. And again, once again, thank you. And so, yeah, stop recording.